Today's presentation is on Dutch-style cheeses, and we're going to be looking at both the technology, the recipes, and also the key process controls, the technological targets, the pH parameters that we need to ensure quality and safety in these cheese styles. I've been introduced just before the start of this presentation, but I'll just say a little bit about myself. I work as a freelance dairy technologist and food safety consultant and cheesemaking instructor. I work in the UK and around the rest of the world. I started out with a degree in biochemistry, which I chose not to use in one of the more conventional ways that I could have used it, and instead went to become a farmhouse cheesemaker. And now I offer technical support to cheesemaking businesses, most of them at the smaller artisan end of the scale. I wrote the Guide to Good Hygiene Practice for the European Commission, which has helped a lot of cheesemakers and other dairy processors around Europe to implement food safety management systems for their businesses. And I've also done a lot of work with the regulators in the UK, training some of the UK food enforcement officers in the application of HACCP principles to small-scale cheesemaking. I'm also the director of the Academy of Cheese, which is setting up a 4-level training program aimed at cheese professionals to give them a much better idea of how cheese is made and the technical aspects, as well as the ability to taste and to talk about flavors. So we're looking at Dutch cheese today, and principally the key Dutch cheese that we're going to look at would be the Gouda style. This is a cheese variety which has a number of different variations. We're going to look at quite a few of these. There are also quite a few similar technologies which are actually originally derived from a Gouda style recipe. And these would include things such as mimolette in France, which is essentially seen as an attempt to copy a Gouda style recipe. First of all, we'll have a quick look at the physicochemical parameters of the cheese, the appearance, and the flavour profile. Gouda would typically have fat in dry matter of around about 48 to 52%, and the typical moisture level in these cheeses would be about 40% in the younger cheeses at least, decreasing over time as the cheese lost moisture. The appearance, we're looking at a closed texture. This is one of the key characteristics of a Gouda style cheese. We wouldn't expect to find a lot of openness in the paste of cheese. When we look at it, we should find that there is very little in the way of open space between one side of the rinds and the other, though there may be some small eyes due to the growth of some of the lactic acid bacteria and the resulting gas development. Some of the variations on this recipe, such as Maasdam, would of course have larger, very round spherical eyes caused by the propionic acid bacteria. We'll look at those variations a little bit later on, but the typical appearance of a Gouda style cheese is not dissimilar to that we see on the front of the course presentation. Very close texture and some small eyes though. The flavour profile will evolve over time, and it would start out being very buttery and very mild when young. It would develop more complexity and more intensity of flavour as it started to mature, and the sweetness of those flavours would begin to come out quite significantly. By the time we get to about 8 months or so, the Gouda should have a predominantly sweet flavour. We would also expect that after this time, we develop a more crystalline texture. We'll talk about the mechanisms of the crystal formation a little bit later on. But this crystalline texture will tend to increase as the cheese loses moisture. There are examples of Gouda-style cheeses being made with cow's milk, sheep's milk, goat's milk, or buffalo milk. I believe there are some Gouda-style cheeses in Mongolia being made with all kinds of weird and wonderful species of milking animal, yak and camel, and anything they can get their hands on, basically. But these species would be the four most common, and we have examples of each of these in the Netherlands. The starter cultures that we would need to use to make Gouda-style cheese are predominantly mesophilic. And there's a starter manufacturer called CSK who surveyed a lot of the farmhouse cheesemakers a few decades ago and started to select some of the best indigenous starter cultures that they were finding on each of the farms. When they studied what was actually growing in those undefined starter cultures, they found that they were almost entirely mesophilic, that there was some Lactococcus lactis, subspecies Lactis and cremoris, but also quite a lot of Diacetylactis and quite a lot of Leuconostoc as well. The Leuconostocs that they found made up to around about 30% of the total population in the starter culture. So essentially we'd be looking for a mesophilic culture, a heterofermentative culture, which means that it's going to produce not just acidity, but also some gas and some aroma compounds, some buttery diacetyl flavors. And this would put us very much in the territory in which we find cultures such as Christian Hansen's Floradenica, or the two rotation cultures for Floradenica, which are CHN19 and CHN11. Or alternatively, if we were looking at Danisco cultures, we might be looking at Probat 222 or Probat 322. Here we would have a level of aromatic or heterofermentative lactic acid bacteria reaching levels of around about 30%, which would give us the kind of gas production that we're needing for cheeses like this. If we were using a bulk starter culture, and I'm not sure how available they are in Australia, but it is possible to get what are called semi-direct starters. In the case of Floradenica, for example, we can buy a powder which is not intended to be used as a direct vat starter, but can be used to make a liquid bulk starter that is essentially the Floradenica bacteria. If we were using a bulk culture, we would add around about 0.8 to 1% of the volume of milk. So if we had 100 litres of milk, we would be adding 0.8 of a litre to 1 litre as starter culture. Alternatively, if we're using DVI, and this would of course be the most common way that starter culture is added, we would probably be looking at a dose of around about 6 to 7 units per 100 litres. And as with all suggestions for starter dose, there can be some adjustment to that. For technological reasons, given the composition of the milk, we might reduce the dose very slightly, or we might have need to increase it very slightly. But this would be a good average value that we would expect to find in a lot of dairies making cheeses of this type. There are some examples of dairies which are adding thermophilic cultures as well. Sometimes these will be added as a flavour adjunct. They can also help to control the acidification to some degree. If we find that our acidification is racing away from us, we can cool the cheeses down slightly and the thermophiles will go back to sleep. Here we might be looking at a dose of thermophiles up to around about 30 or perhaps 40% of the starter dose. But the Gouda style recipes traditionally were mesophilic styles of cheese. The use of thermophiles will sometimes enhance proteolysis and give us slightly more interesting flavors in a shorter space of time. But as with all things in cheese making, if you really want to get complexity in the final cheese, you probably need to do it the slow way. There's no way of rushing flavor development in cheese through the use of unnecessary flavor adjuncts. Next, we're going to look at the process steps, and we have I think 3 slides here in which we'll take the process step by step. So we start off with milk, obviously, and the milk may be subjected to heat treatment. It may be pasteurized. In some cases, in the Netherlands in particular, there's a strong tradition of making raw milk cheeses in the Gouda style. But having heat treated or not, as appropriate, we would then heat the milk to around about 31 or 32 degrees. And after we've achieved this temperature, we would put in the starter cultures, predominantly heterofermentative mesophiles, as I've said, and a typical dose of around about 6 to 7 units or DCUs per 100 litres. We might also optionally add a variety of additives at this stage. So, for example, there's a defect we're going to talk about later on in the presentation, a defect called late blowing defect, which is caused by certain species of Clostridium. If we had the likelihood of Clostridium coming through in milk, we may need to add some inhibitory substance. And this could include things such as lysozyme, which we would add at around about 10 mils per 100 litres. Or we might add some sodium nitrate, which we would add at around about 0.005 to 0.02%. These 2 additives would be used to control blowing where it's present. We'll talk about some of the other ways that we can avoid blowing defects slightly later on. There are certainly some producers who choose not to use these additives, and so they need much stricter control over the milk supply to avoid late blowing defect. A cheesemaker might also choose to add calcium chloride up to around about 0.02%. The calcium chloride is often used to improve the set of the curd, and it's often used where milk is either slightly old or is over pasteurized. It will improve the set. It will never compensate for the fact the milk is old, or the fact the heat treatment has been slightly excessive, or there's been aggressive pumping or something like that that's caused some damage to milk. So we have to accept that calcium chloride can mask the symptoms of whatever has been done to the milk prior to processing, but it's never actually going to reverse those things completely. I tend to avoid the use of calcium chloride wherever possible, and achieve a better set through the use of fresher milk, through much stricter temperature control during pasteurization. And some cheesemakers might be adding annatto, which is of course a colorant. It's based on it's derived from a seed from a South American shrub, something called bixa. And here we would add the annatto at a dose of around about 2 to 10 milliliters per 100 liters of milk. So we would mix up our cultures, we'd mix up any of the additives that we're wanting to put in. And having added the starter cultures, we would leave the milk to ripen for a period of around about 30 minutes or so. There's no real advantage to leaving the milk for a prolonged period of time here, and it actually just increases the likelihood of us overshooting our pH targets at the later stage in the process. Having ripened the milk, we would put the rennet in. We would be looking for about 25 to 27 milliliters of rennet per 100 liters. In the case of cow's milk, we might use a slightly lower dose of rennet in the case of sheep's milk, might use a marginally higher dose in the case of goat's milk. The first signs of coagulation, once again in cow's milk, we would expect to see that after around about 15 minutes. And goats and sheep's milk, the flocculation time would normally be a little bit shorter. The flocculation point is the point at which the milk ceases to be completely liquid and starts to become a very weak solid. And there are a few different ways that we can assess this. We can put a drop of milk into a test tube full of water and we can look to see some flakes forming. At that point, we would say we've reached the flocculation point. And normally we would leave the milk to firm up, to harden for a fixed period of time in proportion to the flocculation time. For a Gouda style recipe, we'd be looking at a ratio of around about 1 to 2 times flocculation for the hardening. So if we have a 15-minute flocculation time and we're leaving the curds for 1 to 2 times flocculation, we would be looking at a total coagulation time here of around about 30 to 45 minutes. And after that, we would cut the curd down to around about 0.5 centimetre smallest and around about 2 centimetres at the largest. And here we start to see some divergence in the way that people are making Gouda style cheeses. Pictured in on the screen, you'll see a large vat with some elliptical style cutters. These have a habit of cutting the curd down to quite a small size. This gives us a curd which drains very quickly, which loses a lot of whey into the vat at a very early part of the cheese making process. Typically, these cheeses will be a little bit drier at the end of manufacture than one of the cheeses which is made with a 2 centimetre cut size. The 2 centimetres will tend to retain a little bit more moisture. So within the category of Gouda, we find different degrees of firmness or relative softness or suppleness, depending on how much moisture is being retained. And one of the things that is going to influence that moisture is the choice of equipment. One of the vats, as we see here with the overhead gantry and the elliptical cutters, it's going to tend to cut the curd down very efficiently, and we're going to tend to end up with much smaller sizes of curd. After we've set the curds, we're going to obviously cut them, and then we need to start stirring and scalding the curd. We would stir for about 20 minutes, having initially cut the curd. And that's going to take off a little bit of whey from the curds. They're going to become a little bit denser. They're going to become a little bit more robust, so we can increase the speed of stirring as we go along. Having stirred the curd, we can run off a proportion of the whey. And this is an integral part of the Dutch style cheese technology. We need to perform what's called a wash of the curd. This is going to help to give us the sweeter flavors that we're looking for in the finished cheese. We would run off around about 20 or 30% of the whey in total, and we would top that up with water. In this case, we're going to use hot water, and through the use of the hot water, we're going to achieve our final scald temperature. The scalding of the curd is something which is going to help to drive moisture out of the curd particles. We scald the curd when we're making cheddar as well. In cheddar making, we go up to about 40 degrees, but in the Gouda makes, we're a little bit below that. We don't want to drive off quite as much moisture as we would do in your typical cheddar make. And we will be looking for a curd temperature of about 36 to 38 degrees at the end of scalding. The use of hot water in the curd washing means that we can approach that final scald temperature incrementally. We would do this by pouring in a small amount of water at a time. We'll see in one of the next pictures how this is achieved. The time to reach the curd temperature, well, it would normally take around about 30 minutes to return that 20 or 30% of the volume of the vat to top that back up with warm water. So the curd washing requires us to remove 20 to 30% of whey. We top back up to the initial level at which the milk was, or the whey was in the vat. By that point, we should be at our 36 to 38 degree scald target temperature. After that time, we're going to pitch the curds, which essentially means that we're going to let them settle down to the bottom of the vat. And we're going to start draining off the whey, initially down to the level of the curd. Then we'll do some pre-pressing of the curds, forcing them to mat together beneath the level of the whey, before cutting them into blocks and pressing them at around about 10 pounds per square inch, or 0.7 bar. And that will be for about 1 hour. We would then turn the cheeses on the press and return them to the press at a slightly higher pressure, about 1.5 bar in this case. And they'll be left on the presses until the pH reaches the target value, which is around about 5.4 down to 5.2, after which time we will put them into a brine tank. So the pictures that we have in the next few slides will hopefully bring to life some of the process steps that we've just looked at in the process flow. The curd washing you see being carried out here. You see in the vat we have some very small, not quite rice-sized curd grains, but maybe just a little bit bigger than rice-sized grains. The cheesemaker has drained off some of the whey from the vat, and now they put this bar along the side, and they have hot water going through the bar. That's pouring onto the curds. The curds will continue to stir around while the hot water is going in, so that each particle of curd is subjected to the same heat treatment for the same degree of time. And in doing so, we achieve consistency in the final cheese. The curd washing, what that's actually doing here, first of all, in removing some of the whey, which will contain quite a lot of lactose, we've removed that lactose from the vat. We top back up with hot water, and that's going to dilute the remaining lactose in the whey. We also have some lactose in the curds, and now we have a diffusion gradient where lactose from the curd will be drawn out towards the whey, where the lactose has now been diluted. And this is going to limit the total acidification of the curd. If we remove lactose, we remove a food source for the bacteria, so the final pH value that we reach will be a little bit higher than it would have been without curd washing. In these next slides, we see the pre-pressing of the curd. So having pitched the vat, allowed the curds to sink to the bottom, we drain the whey down to the level of the curd, and then it will be fairly common to put some heavy steel pressing plates onto the top of the curd, as we see in the very first picture in the top left. The curds will be completely covered with these pressing plates, and that would force them to compact. It would squeeze out additional whey. Then the cheesemaker would come in and cut those compacted curds into blocks, approximately the same size as the cheese molds that they were wanting to fill. The time of pre-pressing would be around about half an hour, maybe 45 minutes at most. And then the cheesemaker will take the blocks, put them into the cheese molds. You'll notice that the cheese molds here are round, the blocks are square. That isn't a problem. As soon as they start pressing, the curd will extrude out, it'll squeeze out to fill the space. We have a lot of calcium in the curd still, and we have a lot of elasticity here. So the curds are able to move and take the final shape once they go on the press. So the final steps in the process, we would brine the cheese. We're looking for a target salt level of around about 1.6 to 1.8% salt. And we'll look at the timings in just a moment. We would allow the cheeses to dry, and then we would apply some plastic cheese coating with or without some natamycin, which is a colorant. We would mature the cheeses typically at temperatures between about 12 and 15 degrees, and we'd be looking for a relative humidity of around about 60 to 80%. It's a little bit lower perhaps than some other cheese varieties, But in the case of Gouda, of course, we're wanting to remove quite a bit of moisture during maturation. We actually want the cheeses to dry out and become a lot harder. So here we go for a slightly lower relative humidity than we would do in the case of a cheddar make, for example. If we're using a mold inhibitor called natamycin in the cheese coat, then we would need to repeat the use of the natamycin in the coating after around about 1 week. The cheese would then typically be matured for somewhere between about 3 and 12 months. And we would turn and rub the rinds each week in order to try and keep them clean. The slides that we see here will discuss the brining of the cheeses. So a brine tank, this is something that can be made up and we can reuse the brine as long as we maintain the right composition within it. As long as we've got a high enough salt level, we shouldn't see the growth or survival of even the more salt tolerant bacteria such as Listeria or coagulase positive Staphylococci. It's not uncommon for a Gouda cheesemaker to keep the same brine for many years, or in some cases many decades. I was working in a farm in the south of England that was essentially making a Gouda style technology, and the brine when I arrived there I think was about 10 years old. But this does require some careful handling and monitoring. So first of all, we need to ensure that we've got sufficient salt in the brine. We need around about 21% weight per volume, which is equivalent to around 20 degrees Beaumet, or a brinometer reading of around about 80 degrees, 80% salt saturation. So 3 different ways that we could measure the salt concentration in the brine tank. And we can do this using what's called a floating brinometer or a salometer, essentially a little glass column that sits and floats in the brine according to the density of the solution. Or we can use a refractometer. This is an optical device in which we would put a drop of the brine onto a little slide, hold it up to the light, look through the eyepiece, and we would see the salt concentration contained within it. When we make up a fresh brine, of course, we need to balance both the calcium and the pH of the brine. To balance the calcium, we would want around about 0.2 to 0.3% weight per volume. If we don't balance the calcium, we'll see what's called a slimy rind defect. We'll begin to pull calcium out from the cheeses, and this will soften the outside, which doesn't give us a firm rind and can cause a lot of damage to the cheeses. They're even being removed from the brine tank. Your thumb can just slip inside the rind of the cheese, and it then makes it very hard to coat and ripen that cheese properly. The first few batches that you put into a brine tank that had inadequate calcium levels would leach calcium and would become soft on the outside. After that, the brine tank would be more stable, but why sacrifice your first couple of batches of cheese if we can just set the calcium level as we need it to be from the start of the creation of the brine tank. The pH will also need to be balanced, and here we're looking for values that are very similar to the target values in the final cheese. The pH of a brine should always be very close to the pH of the cheese going into it. In this case, we need a pH for around about 5 to 5.3, and that will be very easy to measure using a pH meter. We would just need to add enough food-grade lactic acid or citric acid, or if necessary, some whey from a lactic cheese make, until we could balance the pH in that way. The brine tank would typically be held at temperatures of around about 10 to 13 degrees, so most cheesemakers would tend to keep their brine in a part of the storeroom, part of the cheese store, and we would allow around about 6 to 8 hours brining time per kilo of cheese. Of course, every time we take a cheese out of the brine tank, we need to top up the salt that cheese has taken out. So here we would need to take some careful measurements of the salt concentration and top the salt level back up till we achieved a 21% weight per volume again. And we would also need to filter out some of the solids that we would find in the brine. We can do that by scooping them off using a fine sieve if there are small bits of curd floating on the surface. Periodically, we'd also need to empty out the brine tank to transfer it across to another vessel, empty out any of we get a protein sludge down at the bottom of the tank sometimes, so we would need to remove that. Wash and clean, disinfect the tank, and then return the brine over to the brine tank again from whatever vessel would be holding it in. We would typically do that every month or every couple of months, depending on the number of batches per week that were going into the brine tank. It's not uncommon for the brine to take on a slightly yellow, in some cases slightly greenish appearance over the course of time. Of course, that's due to the fact that the cheeses will be leaching out whey into the brine tank. The key thing is that we're keeping an eye on the pH and we're keeping an eye on the salt concentration. As long as we have no abnormal change in the pH value and the salt concentration remains controlled and topped up after every batch, there is no or very little risk of listeria or coagulase positive staph surviving in these brines, though some periodic monitoring of the brine for listeria would be sensible as part of your environmental monitoring. When we come to coat the cheeses, here we would typically use plastic cheese coating. This is a type of polyvinyl acetate, essentially a kind of food grade glue, which is painted onto the outside of the cheeses. Traditionally, some of the Gouda recipes would have been coated in oil. I think there were some historical recipes which referred to the use of linseed oil in coating the cheeses. The plastic cheese coating is a modern alternative to that. It's semi-permeable. It allows some moisture and some gas to be lost from the cheeses. We can also mix into that a mold inhibitor that I was describing earlier called netamycin. And this will give us the nice clean rind appearance that we would typically associate with Gouda style cheeses, including the ones that we have in the picture there. Some examples of the types of cheese coating that are available on the market would be Viplast, which I think is made by Danisco, and DSM have a product called Plasticoat. Both of these products are essentially the same thing, a polyvinyl acetate intended for coating the surface of the cheese. However, sometimes alternative coatings have been used, and there are some examples of cheesemakers who are coating their cheeses in wax. It's not always a good idea. If you coat a wet cheese in a wax coating, there's nowhere for the moisture or for any gas to escape to. So it's maybe not the best option for coating cheeses immediately out of the brine tank. It might be a better bet to plasticoat your cheeses and then wax them prior to sale to the final consumer after a period of maturation. And there's another cheese made in the Netherlands in which the cheesemaker essentially makes according to a Gouda style methodology, but they didn't feel comfortable using what they called wood glue, this plastic cheese coating on the outside. So in their case, they actually smear the cheeses with ghee or clarified butter. We'll have a look at some of those cheeses in a moment on the slide when we look at maturation. So now we need to understand some of the essential process controls to achieve consistency in making Gouda style cheeses. And this is something that I had a great personal interest in many years ago as I arrived at a farm to make a Gouda style cheese that was aged to about 18 months. And I really couldn't wait 18 months to find out if I was a good cheesemaker or not. So I started looking at the pH data for all of the very best and all of the very worst batches that had ever been made on this farm, and started plotting that data. And I found that right at the start of the make, so as the starter cultures were going in, and right at the end of the make when the cheeses were going into the brine tank, there was no correlation with the pH value of the milk or of the cheese and whether it was going to make a good cheese or not. But there was one point partway through the cheese make in which a little gap opened up in the pH curves that we plotted. And this gap showed a significant correlation with whether it made a good cheese or not. You see the gap centered, it's centered right about pH 6.3 or thereabouts. Everything that came in above that gap made a truly excellent cheese, and everything that came in below it was awful. It was weak-bodied, it was over-acid, it was crumbly, brittle, it didn't ripen properly. And this marks one of the key process controls for this cheese type. If we look along the bar at the bottom, we find that it's this change, this difference, this monitoring point is happening at about 5 hours into the cheese make. And at 5 hours in, I was pressing curds and getting ready to put them into the molds and put them on the press. If we can achieve a pH above 6.3 by the time the curds are pre-pressing, just before they go onto the cheese presses, then we're going to make a good Gouda. But if we're approaching 6.3 or we've gone beyond it, we're going to make a weak-bodied or over-acid cheese. We're going to hang on to too much moisture, it's going to be pale in colour, it's going to be chalky, and it's going to be crumbly. Gouda is intended to be an elastic style of cheese, and we need the pH to remain almost in the lag phase all the time that we're taking whey off those curds. Most of the moisture that is ever going to come off a Gouda curd will come off before it comes out of the vat, which is the point at which we're pre-pressing. So as long as we're in that flat phase of the pH curve while we're working with the curds in the vat, we're going to be able to make a good Gouda. And if we're coming into pH 6.3 too quickly, well, we need to take some corrective actions. Maybe we need to reduce the starter culture in the next day's dose, or cut the curds finer, or possibly we need to scald the curd to a slightly higher temperature to drive out more moisture. Or maybe we need to do a little bit more curd washing in order to reduce the total acidification. But pH 6.3 or above, at the point the curds are pre-pressed and then go onto the cheese presses, this is the essential process control that will ensure quality in our final cheese. The pH target that will ensure safety, of course, is the pH that we reach at the brining tank, and that would typically be 5.4 or lower. If we have a pH above that, we need to start investigating why the pH was impaired, why it was inhibited, and why it didn't proceed to the correct value. And we might need to think about some additional microbiological testing to assess the safety of these products, or other corrective actions that we may define in the HACCP plan where the acidification is unsatisfactory. We have various recipe variations that we can discuss briefly. We have other cheeses made in the Netherlands, which are essentially made according to a Gouda-style methodology. Edam would be one example. The significant difference here is that the shape of the cheese is different to a flat Gouda. It's made in a spherical cheese mold. And this tends to hang on to a little bit more moisture at the curd of the cheese and allows for a slightly higher acidity by the end of it. One variation on the Edam theme would be Mimolette. This was essentially reputed to be a French version of copying Edam and Dutch styles of cheese in Napoleonic times. And here, annatto would be added up to a maximum level of around about 50 milligrams of bixin per kilo of cheese. And the bixin level in a standard annatto solution would be around about 1% or so. We'd be looking at typical doses here of annatto of around about 50 to 80 millilitres of annatto solution per 100 litres of milk. We also have flavoured variations on the Gouda theme, and here the flavours, the dried herbs, would be added at the stage immediately before pre-pressing the curd. So we would pitch the curds, we'd drain the whey down to the top of the curd, then we would mix in our herb solutions, our herb mixtures, stir that round till it was well dispersed in the curd, and then continue with the pre-pressing. The herbs would then be entrapped within the curds as they go into the molds. And typical flavours that might be added here would include things like cumin seeds or fenugreek. There's a lot of cheesemakers who are adding mixed herbs, or in some cases nettle mixes. It's possible to buy dried nettle as a herb mix from some of the Dutch ingredient suppliers. And the other variations here would include a smoked Gouda. In this case, the Gouda would need to be smoked prior to putting on the plasticoat. So we would make and brine the cheese, then we would smoke them immediately, plasticoat them, and then take them to the cheese store. And Maasdam style cheeses, which are essentially Gouda's nod towards Emmental. Here we would need to add some propionic acid bacteria in with the starter cultures. We would make the cheese, we would then put them into the cheese store for a period of ripening. Having achieved some initial ripening and having seen the pH starting to rise back up during the ripening of the cheese, they would then go into a hot room at around about 20 degrees. And this would encourage the propionic acid bacteria to start growing and producing the large round eyes that we want to see in these cheese types. Here we see a typical cheese store. In this case, it's the cheese store being used to ripen Remica, which is a modern variation on the Gouda theme. And this is a cheese which is coated with clarified butter, which gives a much more natural appearance to the rind. They're also using slightly different molds that have the stencil around the outside of them. But we see a nice clean looking cheese store. The humidity was relatively low there, so they could pull some moisture out. The cheeses would be periodically brushed and turned without the plastic cheese coating. These cheeses are very much prone to cheese mite, and so we need to keep the cheese room very clean and keep all of the mites vacuumed up. Otherwise, they'll start to cause significant economic losses. Typical temperatures here. Well, for most Gouda types, we'd be looking at somewhere between 10 and 15 degrees. 12 degrees would be a fairly common temperature used by many different cheesemakers. Over the course of time, the populations of bacteria in the cheese will change. Our lactic acid bacteria, you'll see on the graph here, is at rises to its highest level by about 4 weeks into the maturation time and then begins to fall off a little bit. This data is taken from a study that was carried out on the Gouda style cheeses in Poland. The starter lactic acid bacteria are the predominant organisms which make up those lactic acid bacteria at the start of ripening. But we'll see the yellow line here, which is our non-starter lactic acid bacteria. These are wild type lactic acid bacteria, which are present in the case of pasteurized cheese as a post-pasteurization contaminant. We find them growing in pasteurized cheese just as much as we see them growing in raw milk cheese. And because they're a little bit more salt tolerant, they'll tend to rise to dominance, and they'll tend to they'll tend to be the most dominant lactic acid bacteria by the end of ripening. After about 12 weeks in this study, we saw that the non-starter lactic acid bacteria were the principal starter lactic acid bacterial organisms there. We also find in Goudas that yeasts will tend to increase during the early part of the ripening time, but tend to tail off a little bit after about 8 weeks. Here, the yeast will help with some deacidification, and they'll help a little bit with some rind development, but it would be very uncommon for a cheesemaker to add yeast deliberately. These, once again, are all present as post-pasteurization contaminants, and we can see them as representing an indigenous microflora within the dairy that will give cheeses their own unique flavor, even when we're working with pasteurized milk. The common defects that we'd have here would include things such as late blowing defect, which we'll see on the next slide, mechanical openness, and rind rot. Mechanical openings are where we haven't pressed the curd significantly below the level of the whey, and we've allowed some air to be trapped within the curd. And this can easily be avoided by better pre-pressing and keeping the curd below the level of the whey up until the point of pre-pressing. Rind rot can be caused by soft curds around the edge of the cheese. The best way to avoid this is to ensure that each of the curds are treated to the same degree of heat treatment during the scald. If we're consistent in that and we're consistent in our size of cut, we shouldn't have excess acidity in some bits of curd compared to others. Excessive acidification is another common defect, and here we need to make sure that we've got those curds on the press before a pH of around about 6.3. Unlike cheddar, crystal formation in this case, so the conversion of L-form lactic acid into its mirror image form, D-form lactic acid, that's to be expected because we're using starter cultures that are specifically chosen for their ability to form D-lactic acid. So crystal formation in these cheeses is very common and isn't a defect in this case. An associated issue that we sometimes see is crystallization of the D-lactic acid on the cut face of the cheese. Sometimes a cheesemaker will have some cut wedges of cheese returned to them by a retailer with complaints that there's mold growing on the surface. In many cases, this is actually the D-lactic acid starting to crystallize on the cut face. And this will happen because of small imperfections on the knife or wire used to cut the cheeses. In this case, once again, it can be an expected part of the cheese technology, and it may be worth putting on the label that sometimes some natural crystallization can occur within these cheese varieties. Late blowing defect is probably one of the most significant issues that we have with Gouda style cheeses. And here these are caused by heat stable Clostridium species, including Clostridium tyrobotaricum and Clostridium sporogenes. And these are spore-forming organisms that will survive pasteurization. They're associated with the use of silage. So one of the principal ways to avoid them is to avoid the use of silage. Of course, within silage, we have very many different quality standards in production. Silage which is poorly made or which is made on uneven ground where there's a lot of inclusion of soil, for example, we'll see more spores in the silage or surviving in the silage, and we'll see more of an issue in the cheese. And this can be controlled by the use of lysozyme or nitrate, or by starter cultures which produce an antimicrobial agent called nisin. It can also be inhibited by effective salting. Undersalted cheeses will be more prone to late blowing defect than the correctly salted cheeses. So these are things that we can do to try and prevent it. But there's one other step that we can take to try and reduce its likelihood as well. If we absolutely have to feed silage, we would have to accept that there are going to be some spores present and they'll make it into the feces of the milking animal. And if there's any fecal contamination of the milk, that is going to introduce the spores back into the milk. So significant attempts to reduce fecal contamination during milking can actually have a positive impact on reducing the incidence of late blowing defect. Taken alongside a reduction in silage use wherever possible, and other controls such as correct salt levels or the use of inhibitory substances such as lysozyme, we should be able to reduce the likelihood of this happening. What we see in late blowing defects are a lot of splits within the cheese, a lot of large, uneven holes, and typically a flavour taint. We see the development of a lot of butanoic acid, which is the flavour that gives vomit its particularly memorable flavour. It's not normally a desirable flavour component in many cheese varieties. So late blowing defect can cause a lot of economic losses here. The next few slides, I'm not really going to go into in any great depth, as you'll all have copies of the PDFs from the presentation. But I've given you some of the specifications for the cheeses made in the Netherlands with geographical indications, which gives you an example of some of the coagulation temperatures used, some of the pH targets that they're looking for, and some of the salt levels, as well as maturation times for some of the PDO, PGI, and the farmhouse TSG cheeses made in the Netherlands there. And we also have here some of the specifications for things like the Edam style cheeses. And we see that compositionally, at least, the cheese is not dissimilar to some of the Gouda style recipes. The significant difference in the Edam style cheeses would be the fact that the cheeses are simply round. So that brings us to the end of the presentation. There's been a lot of information to fit in. So I just need to see if we've got any questions here.
Yep, we have got a few there, Paul. So thank you so much. That was really, really excellent. And I hope people have got a lot out of that. Okay, so have you managed to open your box?
Yep, I'm here. Okay, so from Alice, what IMCU is your rennet dose based on? Yes, sorry, I should have said that actually. 140 IMCU, so standard strength rennet. So if you were wanting to convert that into a different strength of rennet, you would multiply the rennet dose that I've given you by 140, and you would divide it into the strength of your own rennet in IMCUs per milliliter, and that would tell you how many milliliters of rennet you would need for your specific type of rennet. The next question from Alice, which specific organisms are responsible for late blowing? So hopefully we covered that at the end of the slide there, but we're looking at species of Clostridium, Tyrobutyrichum, and Sporogenes would be fairly common organisms causing blowing defects. The next question, do you see much natural rind Gouda? Very little, actually. So the makers of Remica are probably, they're quite an unusual farm. There's not many times that I would go and visit a dairy and come away feeling that I had learnt a hell of a lot more than I knew before I arrived. But their farm was one of those farms. And they take a very radical and different approach to making their cheeses. They wanted the cheese to be as natural as possible. And they had a lot of fat coming off on the presses. They were using Jersey milk. They decided that it would make a lot more sense to make clarified butter, and then they started thinking, well, how can we use this clarified butter to coat our cheeses? That wasn't without its problems. They had a lot of mite problems initially until they increased the amount of brushing and turning to get on top of the mite issues. For that reason, it is a lot more common to see the plastic cheese coating, and it's a lot easier to use. it takes a lot less work in the ripening of the cheese and keeps the outside of the cheese looking incredibly clean and shiny. The outside of the Remaker, by comparison, has the growth of a lot of surface molds. It doesn't look at all like a typical traditional Gouda style. What they've essentially created is something very different along the Gouda methodology. But it will be more common to see the plastic cheese coating, and it does make it a lot easier to look after. The cheeses just need a wipe with a cloth every, say, couple of weeks or so once you're turning them, in order to try and keep any surface molds from growing on the surface. And as long as you've hit your pH targets during the cheese make, and you've not over acidified, they shouldn't be too prone to surface molding. Common cause of increased non-starter lactic acid bacteria in pasteurized milk. So the non-starter lactic acid bacteria, these are going to come in from a variety of different sources. First of all, there are some that are a little bit more heat stable than others. And there's certainly some examples of non-starter lactic acid bacteria associated with histamine formation in cheese that seem to be able to survive pasteurization, even at low numbers. Now, these organisms would come in due to inadequate cleaning of the milking equipment or pipework and things like that. So improvements to cleaning of the milking machine or storage tanks or pipework can reduce these types of non-starter lactic acid bacteria. Others are not associated with histamine formation. These would include things such as Lactobacillus rhamnosus or Lactobacillus cavatus. They would tend to come in as a post-pasteurization contaminant. And the dairy is a wet environment. There's going to be a lot of milk residues around. There's a lot of places that some non-starter lactic acid bacteria could hide and thrive, including in the cheese molds sometimes. In the case of pasteurized cheese dairies, we see just as many non-starters rising to dominance as we would see in raw milk dairies. So we just have to accept that somehow a very low level will get into the milk. And the conditions within the cheese, the salt level, the acidity, this gives a selective advantage to these wild type non-starter lactic acid bacteria compared to your starter cultures, which we know have been selected for their salt sensitivity.
Okay, so I think we've got three questions there from Lydia and Carla. So
okay, so if we look at the acidification curve, the desirable time to reach pH 5.4 to 5.2, we're probably looking at around about 4 to 5 hours. Starter culture would go in, we'd be looking at 30 minutes there, we'd be looking at around about another hour to set the curd using rennet. Then we've got our period of cutting, stirring, scalding. That's going to take at least another hour. Yeah, I'd say at the very earliest about 4 hours. 5 would be possibly a much more realistic target. The calcium levels in the brine would be very difficult to measure. And you don't need to top that up. It's really just as you're making a brine up to begin with, we would need to dose in a small amount of calcium chloride into the brine tank in order to prevent this slimy rinds defect. But having set the brine up, we need to top up salt. Generally, we don't need to top up calcium, and we don't need to adjust pH in most cases. It is uncommon to add yeast simply because the yeast are going to be naturally present in the dairy environment. In the same way with a Stilton style cheese, for example, the cheesemakers there don't add yeast, but if we got a microbiologist to survey the populations inside a Stilton, it's absolutely full of yeasts and a huge diversity of them. They're all coming from the dairy, and Stilton is a pasteurized cheese as well. So these are accepted expressions of the microflora of the dairy, I suppose, if we want a romantic way of putting it. And we see them just as much in pasteurized cheeses. If we were to add yeasts, well, it doesn't mean the yeast we would add would actually do anything. It may not be able to survive in the conditions within the cheese. The wild type organisms tend to be a little bit more robust and resilient than the starter cultures which are made commercially. So we can accept that there are always going to be natural yeasts present and that they will have some impact on the flavour of our cheese. And yes, so yeah, the final question, was it because it grows naturally in maturation? Yes, absolutely. And we should also try and avoid this idea that pasteurized products are somehow sterile or, you know, that don't express the microflora of the dairy. This just isn't true at all. They're not a sterile medium. And there are certainly a lot of organisms that we'll find in a pasteurized cheese that have come specifically from the dairy.
Wow,
okay.
Thank you so much, Paul. You've really earned your stripes today. You've really demonstrated how thorough your knowledge is of Dutch-style cheeses. So thank you so much.
That's all right.
I'm sure if anybody has questions to ask in the coming week, Paul will be happy to help out. So you can email
Absolutely.
me. Yep, you can email me and I'll put you in touch with Paul, not a problem. Also, we'd love any comments from you on how you found today's webinar, not only for Dairy Australia, but also for Paul, because he can't see your faces and he would really like to know how you're feeling, how much you've enjoyed the webinar. So thanks, thank you, Alison. Okay,
I'd say that's maybe one of the strange things about giving a webinar to people on the other side of the world. You get about halfway through and you do wonder if anyone's still listening or if they've gone off to make a cup of coffee.
Okay then, everybody says that and it's the way it is, but we're very fortunate to have you, Paul, and we really appreciate it.